Welcome to the presentation for the paper titled Beyond Modeling, NLP Pipeline for Efficient Environmental Policy Analysis for the Fragile Earth 2021 workshop. My name is Sharma. I am an undergraduate junior studying computer science. This research is a collaboration among World Resources Institute, Omdena, and Data Science for Social Good Solve. In this presentation, we will talk about the different problems present in restoration policy analysis, the knowledge management framework we propose to address the problems, and then also discuss the different components of data collection and processing, model engine, and the knowledge graph. I will then go over the core advantages of the knowledge management system and then conclude. Our research involves the 2030 Agenda for Sustainable Development launched by the UN General Assembly in 2015, which addresses global problems such as environmental degradation. We believe that robust and transparent policy analysis is key to achieving the environment-focused sustainable development goals. This page is an example of what an environmental policy looks like. As you can see, a policy document is packed with a lot of important information in a very small amount of space. And sometimes when the policy document uses multiple columns, it becomes even harder to understand. Policy analysts are supposed to analyze not one, but tens of such pages in the smallest of policies, which makes policy analysis as a task extremely challenging. Imagine if you need to go through 50 pages, such as this one, looking for discrete information pertaining to a specific policy, such as time, place, incentives, disincentives, deadlines, and then relate this to the interested parties and formulate an action consequence pathway. That would be a difficult and time-consuming task. So what we decided to do through our research was identify and address three major problems in policy analysis. First, time and resource intensity. Governments and consulting organizations rarely have employees whose sole responsibility is policy analysis, and the analysts they do not have the adequate amount of time to conduct a full-scale analysis in a short time frame. Next, information accessibility. Environmental policy as a field lacks the central resources from which relevant policy information, such as the actors and incentives, can be retrieved. And last, overlapping sectors and jurisdiction. To effectively analyze cross-jurisdictional and global environmental policies, one must consider how such factors affect competing and implementing policies. So our core solution to these challenges is a central knowledge management system that brings together state-of-the-art natural language processing techniques in an end-to-end pipeline. The objective of this pipeline is to collect and process policy documents and present relevant information from them to policy analysts. In the next slides, we will go over the different components in more detail. Let's first start with data collection. In this component, we use APIs provided by federal and state-level government agencies where possible, and use web scraping to retrieve environmental legislation documents for US, Mexico, Latin American countries, and India. Next comes the document processing component of the pipeline, which addresses the challenge of information accessibility by building a central database of policy documents in a searchable manner. In this component, we take a document and process it based on whether it is a PDF or HTML. If it is a PDF, we use AWS TextRack, and if it's an HTML document, we use HTML selectors and Beautiful Soup to convert the document into a text file. Then we use the NLTK package to parse the document into separate sentences. A few important points to mention on parsing the documents on a sentence level. Useful pieces of information such as financial incentives and named entities appear at a sentence level in policy documents, and many of the NLP models we use further in the pipeline have a sequence limit. For these reasons, we parse the documents on a sentence level. Now, here's an example from the Florida Longleaf Pipeline Private Landowner Incentive Program. This is an excerpt from the technical guidelines that I will be using to explain which types of information our pipeline can extract. Now, coming to the model engine component, the pipeline contains three major natural language processing models. The first one is the sentence classification model. For sentence classification, we use the sentence BERT model, which is excellent at computing sentence level embeddings. The goal is to identify financial incentives such as tax benefits, direct payments, loans, fines, supplies, and technical assistance through sentence classification. For this model, both sentence BERT and cross encoders perform well. And at inference time, we pass the sentence embeddings from the sentence BERT model into a random forest classifier for classifying sentences. This model addresses the challenge of time and resource intensity by vastly reducing the amount of time it takes to retrieve the relevant financial incentives present in a policy. Now, coming back to the excerpt we saw before, the sentence BERT model would highlight incentives present in these paragraphs, such as this instance that talks about direct payments to landowners to implement the recommended restoration practices. Now, the second component of the model engine is named entity recognition. For named entity recognition, the first question is, why is it necessary? Financial incentives are commonly used in policy programs. We need to know who is implementing a policy and who does it target. For this, we can use named entity recognition and relationship extraction to answer such questions. We found that transformers lead the way in modeling, especially in the case of policy analysis where relationships among entities are not always explicitly stated in a sentence. For example, one can use the Hugging Face's Luke model implementation for both NER and relationship extraction. By highlighting relevant entities and their relationships with each other, this model engine component focuses on addressing the challenge of overlapping sectors and jurisdictions. Now, in the same policy view as before, the named entity recognition model would highlight the different entities present in the policy, such as the US Department of Defense and the National Fish and Wildlife Foundation, which provide the financial assistance and communicate with other entities, such as the Florida State Service, that enforce and verify the requirements to collect the incentive money. Next, the final component of the model engine is topic modeling. The first question is, why do we need topic modeling when we already have sentence classification? The problem is, even if we know the category of the financial incentive, we still do not know how or where exactly it will be applied to in the real world. Type of incentive in itself is not enough information to act on. So approaching topic modeling from a classification perspective allows it to be more reliable and scalable to tens of topics. We use a sentence BERT here as well. Expanding the information policy analysts have about incentives, this component addresses both challenges of information accessibility and overlapping sectors and jurisdictions. In the same excerpt, the topic modeling model will highlight sentences that contain details about the use of incentives beyond just their category. Here, the policy outlines the ways in which the direct payments are sanctioned to be used, such as in-site preparation and herbicide application. After the model engine is the centralized knowledge graph component of the knowledge management system. The knowledge graph is useful to organize all the different kinds of information we retrieve about the policy documents, such as the government entities, financial incentives, topics, and different relationships among these concepts. Building on top of the Wang et al. Paper, we designed an ontology to structure semantic data and concepts such as classes, their attributes, and relationships specific to restoration policy analysis. Extracting useful information from policies involves creating a pathway between the actors involved in the specific policy act, the jurisdiction the policy covers, and other relevant and restricting information that might be useful for the stakeholders. Some of the advantages of the knowledge management system are that while the pipeline was used on restoration policy analysis in our experiments, it is designed to be applicable on any other environmental focused sustainable development goal, as long as domain experts make the necessary adjustments in data collection, data processing and labeling, and the knowledge graph design. Next, the model engine is designed to work on policy documents of many languages, since most state-of-the-art models are pre-trained on numerous languages. The platform used to build the pipeline is agnostic as well. Any open source or commercial tool can be used to build the different components. For example, the pipeline could be also adapted to track the progress of agreements like the UN Framework Convention on Climate Change. In conclusion, manual policy analysis is a time-consuming and resource-inefficient task, but the purpose is vital for sustainable development. We conclude that the three challenges that we have identified are addressed through our proposed knowledge management framework that retrieves, processes, and extracts highly relevant information from policy documents and presents them in an understandable and actionable way to policy analysts and their stakeholders. That brings us to the end of the presentation. Thank you for your attention.